Hi there, folks. Today we're looking at relations and functions and kind of the difference between the two. And we'll also talk about domain and range a bit as it relates to relations and functions. So a relation is just a set of ordered pairs, just input and output values. Remember, ordered pairs are x comma y, the x coordinate followed by the y coordinate. And for math, for algebra, we a lot of times use x and y to kind of denote those things, but really it's input and output. It doesn't have to be x and y, all right? In science class, it could be two completely different variables. We align those to x and y like we do in math, but it's really just input and output. For algebra, input is x, output is y, okay? And keep in mind, a set of ordered pairs can be expressed in a lot of different ways. We can express ordered pairs literally as ordered pairs, or we could express them in a table, or we could express them in a graph, all right? And when we draw things like lines or curves or that kind of stuff on a graph, it's really just an infinite number of ordered pairs all kind of strung together, almost like beads on a necklace. They're all kind of touching, so it forms that uniform curve or that uniform shape, all right? Domain is just the set of the input values. And again, for our purposes in algebra, typically that's x. All right. So typically that's x for us because those are the input values. The range is a set of output values. And again, typically for algebra, that's y because y is the output values. But again, depending on the situation, input might be something like d for distance, and output might be something like time, which means the function is kind of showing us the relationship between distance and time as it relates through something like velocity. So keep that kind of stuff in mind. We almost always refer to it as x and y in algebra, but make sure you understand that x is just the variable we choose. It's input that we're concerned with. Y is just the variable we choose. It's output we're concerned with, okay? For example, if I look at something like this guy, the domain, again, is a set of input values, which for us are the x values. When we list the domain, if it's a list of numbers, we want to try to list them in the appropriate order. So here's how I'm going to denote this. I'm going to say x such that. So I'm defining what the input is. In our scenario, the input is x. All right. And again, if this was something else, it was distance, I would say d such that, the distance such that. Here are my options. All right. So it's x such that. And now I list my options. So I just list all the x values that I see here. Which is -3, 0, 2, 9, and 23. And they were already in the appropriate order for me as I wrote them down. All right. Make sure you put them in ascending order. Don't just randomly write them down. Makes it easier to read. And then the range for our purposes this time, they're just y values. These are just x, y values. So I'm going to say y. I'm telling you that it's a y value such that. And then once again, I'm going to list these. So I see a -99, a -18, a 0, a 7, and a 14. And again, I list them in order because it makes it easier to sift through. All right? If I look at something like this guy, again, this is still a set of ordered pairs. We just have them listed in a table this time. So I'm going to say, all right, well, I'm going to define the domain. It's x values this time, so x such that. And now I list the x values. So I've got -3, 3, and 4. Notice I do not write the 4 twice because, again, it's already represented. I just want to know which x values are being used, not how often they're being used, okay? The range, in this case, it's y, so I say y such that. And then I've got a -1. I want to do an order here. -1, a 3, and a 4. And once again, I don't list the -1 twice. I just want to know that I use that value, not how often I'm using it, okay? If I look at something like this guy, once again, from our perspective, we don't know what this represents, so I'm just going to call it x and y. I'm being generic about it. So I'm going to say the domain is x such that. Now I have to describe the x values. The problem is that, remember, when we have all of these things kind of connected, this is an infinite number of ordered pairs being connected. That's what forms this curve. Well, I can't very well list every single ordered pair that's here, okay? I can't list every x value, so I have to kind of think of it. And as I come around this curve, I've got like an x value of 3, and then the x value is going down. It's hitting all the decimals. See if I trace this thing. It's hitting all the decimals. It gets to this point at -4, and then it turns back around, all right? So it started at 3, it curved back towards -4, and then went back up to 3. So I just have to think about, well, which x values are being utilized here? So I always go, again, from least to greatest, just like I did before. The smallest x value being used, think about how far to the left this thing goes. The smallest x value being used is back here at -4. So now I have to think about the biggest x value being used. Well, keep in mind this arrow on the end of this guy, let me make it a little bigger. This arrow means this thing keeps going forever, which means the x values are going to keep getting bigger and bigger and bigger. So I would say the biggest x value would be infinity. All right. And so what we do here is I can't list all the values from -4 to infinity. So use an algebraic expression to say that, which would be x is greater than or equal to a -4. And if you think about that, that means starting at -4 and going up forever. Okay? If you're familiar with interval notation, you can use that as well, going from -4 to positive infinity. Interval notation is something we'll look at a little bit later. If I talk about the range, same kind of thing. I'm generically using y, so I define it. I say, hey, I'm doing y, so y such that. And now let's talk about the y values, thinking about it from least to greatest. Well, this thing keeps on going down forever, right? It's going down very slightly forever and ever and ever. So the smallest y value is down at -infinity. It keeps going down forever. But then the biggest y value is up here, 1, 2, 3, 4, 5, 6. Okay? So now I have to think about an algebraic expression that shows me all the values from -infinity to +6. And so this time we're going to use an inequality, but it's going to be a less than or equal to the 6. Okay? And again, if you're using interval notation, if you did that in Algebra 1, you can apply that here and say, oh, it goes from -infinity to +6. Okay? It's another way to list it. Again, we'll look at interval notation a little bit later. All right? It's good to practice utilizing inequalities to describe things, because I think we breeze over inequalities and we don't truly understand how they work. So again, just express it as an inequality. Which x values are being used, which y values are being used. Let's talk about a function. A function is basically a relation in which every input has exactly one output. Every domain has exactly one range. If one of the input values could potentially give us two different output values, then it's not a function. Okay? For example, if I look at something like this guy, I'm looking at the inputs. Right here, I have an input of -3, I have a 0, a 4, and a 2. And just think about it. Does every one of those inputs go to one output? Do any of the inputs have two different outputs? In other words, -3 goes to a -2. Is there any place where -3 goes to something else? 0 goes to 1. Is there any other ordered pair listed where 0 has a different y value? 4 goes to the 7. Are there any 4s that go to something else? 2 goes to a 1. Are there any 2s that go to something else? And so as we look at this thing, all of those x values have their own separate y value. There's no x value that has two different y values. So yes, this one is a function. Okay? Guess I'll write function here. Yes, it's a function. Okay? If I look at the next one, same kind of thing. Start looking at those x values and say, do any of these inputs have different outputs? And so I start with this one. I say, okay, a 4 goes to a -1. Are there any other 4s here that go to something else? Well, yeah, right here. Here, 4 goes to +1. That 4 is going to two different y values, so it's not a function. Okay? And that's it. If every x has exactly one y, if every input only has one output, it's a function. If an input has two different outputs, it's not a function. Okay? From a graphing perspective, we can use the vertical line test to do this. Okay? When I take a vertical line is like an x equals line. So I'm basically just showing the y values at every x value by dragging a vertical line across here. So if that vertical line touches 2 points at once, it means that particular x value has two different y values. That input has two outputs, then it wouldn't be a function. But if it touches 1 point at a time, it's showing me that, hey, when the line is here, the x value has this y value. And as I move it, it's showing me one y value at a time, which makes it a function. For example, if we look at something like this guy. Again, I'm just going to drag this thing across. And so like here's an example right here. I'm at the x value of -2, and my vertical line is touching at -3. See, that's showing me the ordered pair, the x and the y, the input and the output. And notice the input only has one output because it's only touching 1 point. if I went here, same kind of thing. That's the x value of 0, and it's touching the function down at -5. So that's the ordered pair 0, -5, and that 0 only has one y value. And so as I drag across here, it's touching one point at a time. So this one's a function because it touched one point at a time. So yes, this one's a function. Out of curiosity, let's state the domain and range of this thing, just because we need the practice. So I'm generically talking about x, so x such that, think about the x values. Now see those arrows on each end, so it keeps going to the left forever, keeps going to the right forever. So the domain is, well, everything. It's every x value. Every x value will eventually be used. So you can just say all real numbers. And there's the symbol for all real numbers. Okay? And then the range is y such that. Again, think about the y values. The thing goes up forever, but it doesn't go down forever. The smallest y value has that -5. So y has to be, oh, I should try using a marker instead of an eraser, right? Y has to be greater than or equal to a -5. Okay? If I look at the next one, again, take that vertical line. Let's do the vertical line test. And something like right here, see, there's an x value of -6, and I'm touching the y of 0. So that's one value for my y. So right now it appears to be a function, but as soon as I jump out to something like these guys, here's a good example that's easy to read. I'm at an x value -1, but it has a y value of +3. It also has a y value of -3. It's got two different y values at that spot. So this one is not a function. And once again, let's do the domain and range for the practice, because we love it. So the domain, I'm going to say x such that. We'll think about the x values this time. It looks like I have the smallest x value I have is a -6, but then it goes up from there. Look at those arrows. So x is greater than or equal to a -6. And then the range. And if you remember interval notation, feel free to use it. We're going to stick with this set builder notation for now. Y such that, well, if you look at it, it's going slightly up, and the arrow means that continues. It's going slightly down, and the arrow means that continues. So eventually, it's going to keep going up forever. It's going to keep going down forever. So all real numbers. Okay? If I look at this one, again, let me grab my vertical line. All right, so I drag this vertical line across. There it touches 1 point. Here, 1, 1, 1. Right here, it's touching 2 points. So at that x value of 2, I have two different y values. All right, so this one's not a function. And I'm not going to worry about doing the domain and range this time because it would just be listing the ordered pairs. And while that would be practice, it's the tedious kind of practice that we probably don't need. So let's jump to the next one. It's when we have functions that are graphed like this, or relations that are graphed in this kind of manner that we want to practice. So here we go. See, touching 1 point at a time. So every one of those x values has one y value. So this one is a function. I'm going to abbreviate. Okay. And now just for the practice, let's do the domain range. I'm going to write it down here because I'm running out of space. So x such that, think about the x values. Look at those arrows. Keeps going left forever, keeps going right forever. So it keeps going forever in each direction. So all of the x values are being used. So it's all real numbers. And then the range. Again, we're talking about y, so y such that. Now look up and down. It goes up forever. If I look at the arrows, it goes up forever, but it doesn't go down forever. It only goes down to -2. So think about the y values being used. The smallest one is -2, but then it goes up forever. So that's y is greater than or equal to -2. Okay? But again, functions, every input has exactly one output. If you have an input with different outputs, with more than one output, then it's not a function. Okay? And you can do that by looking at the ordered pairs or by looking at the graph and using the vertical line test. Let's talk about function notation. Last thing in this lesson. Function notation, instead of listing the input as y, we're going to list the input as f of x. Okay? And at the beginning of this lesson, I said, when we're talking about domain, it's the input and range is the output. All right? In algebra, yeah, we typically use x and y, but that is just arbitrary. All right? We chose x and y. It could have easily been h and g. All right? So we're just switching up when we're saying x is still the input, but now we're going to use f of x as the output. And listen to how I read this. This is f of x. That is not f times x. All right? In your head or out loud, say, this is not f times x. It's f of x. Yes, it looks like multiplication, but it is not. We read it as f of x because I said so. All right? And this is where students get a little confused. They start to look at it as multiplication. It's not. It's f of x. It's the function. See, f stands for function, kind of. Even though we can change that, it could be the function g. But we label the function in terms of a value like f or g or h. So it's the function f based on values of x. Okay? So it's kind of showing me it's the function f with input of x. For example, if I look at like y equals 3x plus 2, that's the same as saying f of x equals 3x plus 2. All right? And when we look at the first one, x is the input, y is the output. When we look at this one, x is the input, f of x is the output. See, but what's nice by saying f of x, we're saying, hey, the function f, and it's telling us by saying f of x, it's telling us what the input is. It's telling us that the input is x. For example, if I look at something like this guy, f of x equals 3x plus 2. If I were to ask you to find f of 1, see, f of x means the function with input of x. And see, when you input an x, you'll have an x in your equation. But now I want f of 1, so it's telling me that the input is 1. So that just means, hey, plug a 1 in. Ready? See, now instead of having x as my input, I have 1 as my input. All right? What's in the parentheses is what you put into the function. It's the input. And now I just simplify. That's 3 plus 2. And 3 plus 2 is 5. Right? And here's the thing. I can see the input and the output. I can see the ordered pair at the end of this thing. I see the ordered pair 1, 5, and that's significant. All right? It allows me to kind of see the input and the output as an ordered pair right here at the end. Okay? If I look at the next one, same kind of thing. Saying, hey, g of x, so the g function has an input of x values. And look, the function has x values. X squared minus 2x plus 4 is telling me that x is the input. But when it asks me to find g of negative 2, it's saying, hey, make negative 2 the input. So right here, replace this with a negative 2. We're plugging in. It's substitution. All right? So now negative 2 is the input, and I can simplify that. And always use parentheses when you plug things in. This is a positive 4, plus 4, plus 4. That's a lot of force. So I get a 12. And notice, input, output, I can see the ordered pair, negative 2, 12. Okay? And so now we might do some of this in our heads. Ready? Let's see if we can do this one in our heads. I want the g function, and I'm plugging the 3 in. So plug that 3 in, and I'm plugging it into the g function. Make that the input. See if you can do it in your head. Go through the mental process. 3 squared is a 9. 2 times 3 is a 6. 9 minus 6 is a 3, plus 4 is a 7. Okay? And again, if you can't do that, that's okay. Write it down. But you want to start to do some of these things in your head. Not too much. All right? Doing too much in your head will really get you into trouble. But we want to do some of this mental math stuff in our heads. Okay? But once again, I can see the input and the output as my end result. I see that 3 was the input and that 7 is the output. Okay? Same thing, negative 4 this time. If I can jump back up just so I can see it. Again, plug that negative 4 in. 3 times negative 4 is a negative 12, plus 2 is a negative 10. And see, I could jump right to the end result and say, oh, f of negative 4 equals a negative 10. All right? If you need to show it, that's okay. Nothing wrong with that. But it's all right to start to do some of these things that you've done forever in your head. Okay? And then the last one, I want to change the input to 2a, which seems weird, but sometimes x is not the variable we want, and sometimes we want to maybe double that value. I don't know. So the input can be anything. It doesn't have to be a numeric value. So instead of x, I'm going to do a 2a. So I'm just changing all the inputs to 2a instead of an x. And now I simplify. If you remember your rules of exponents, you'll get a 4a squared there. Whew. Once again, that's a lot of 4s. And that's all I can do. I can't simplify that any further. All right. But again, I'm just changing the input. Okay. The g function had an input of x, and I changed those inputs to 2a's. Okay. Here's each of my answers. Whew. But again, function notation. It's all about input, output. All right. What we started with today. If I look at something like this guy, widgets are available for $25 each with a flat shipping fee of $6.50. Write a function that models the situation. What is the cost of 9 widgets? Again, I want to do it in function notation. So I just choose variables that make sense. All right. So like my cost, all right, because it asks for the function that models the situation. So maybe I'll say the cost or the price. So maybe I'll do C for cost based on the number of widgets equals, well, it's $6.50 per widget, so 6.5 times W plus the $6.50 for shipping. Oh, sorry, $25 per widget. These are expensive widgets. $25 per widget plus the $6.50 shipping. Okay? And here's the thing, you could have chosen maybe P for price, the price per widget. All right? But now I can see the situation mapped out using function notation. The cost based on widgets is $25 per widget plus $6.50. All right? It should make sense when we read it as a sentence. Okay? And now the cost for 9 widgets is saying, oh, what if the input is 9 for the number of widgets? So now I plug the 9 in. Okay, and this is a job for your calculator, or you can do it in your head. Let's see, that's 225. Oh my goodness, that was an ugly looking 2. I can do better. Plus the 650. Let me write it up here. So again, C of 9, the cost of 9 widgets, see it's reading as a sentence, is $231.50. Okay, so again, relations versus function, a relation just ordered pairs expressed in a variety of ways. Okay, a function is when all of those inputs have exactly one outputs. We talk about the inputs as the domain, the outputs as the range, and then function notation is just displaying that input-output relationship. Okay.